Questions for me before we jump in? Yeah.
For the homework, I think it's question 1 or 2. There's two systems in both directions.
Mm-hmm. For the seismic loads.
For the seismic loads, once we go through, do we just add those together to get like the total shear force, or?
So, because you're talking about the R factor, the shear, the seismic shear, the base shear.
I forget exactly, but I think I went through it all, and then you get like the total shear before going to the individual floor.
Okay. Yep.
Do you just add that together to get the total, and then do the vertical distribution?
For the so first let me clarify one thing. So the two systems, and I thought I had the homework pulled up. Maybe it's in this other document. Okay, so for this problem, it says each direction has two systems, right? So so you don't have to consider two separate directions. You only need to consider one. All right, so I just wanted to clarify that. And then the difference between those two systems is going to come into play with that R factor, right? So remember what we talked about in class with that is, we'll find that, or maybe it was in the slides. So it must have been in the slides, which I don't have handy, and I don't want to fish through my files of slides right now. But basically, if you go through the slides or the reading and stuff, when we talked about the R factor, and I think I should have, so this table, right? This was from the example in class, but you'll look up two different R factors, and we want to use the smallest one in our calculations, because the smallest R factor is going to be more conservative. It will give us a larger base shear. So use that.
So after you get R, you just proceed with that?
Yep, you pick one R value for the direction that you're considering, and you do base all of your calculations on that. Yeah. Good question. Others? Yes.
Are we allowed to use screenshots for this one in our given statement?
Yeah, since you've got the floor plan to work with, I'll accept that. Yeah. Any other questions? Okay. All right, good deal. So reminder that homework is due Wednesday. And we have 1 week until the exam, so morning. So this week we're going to wrap up the environmental loads lectures. We'll continue with snow loads today, and then probably Wednesday we'll start rain loads. I don't think we'll start talking about rain loads today, maybe, but we'll see how it flows. And so I wanted to take a moment to point out exam logistics. So I just posted this file on D2L. You can find it in the exam info folder. And it's just 2 pages, but it's got the usual information up at the top, what is in the scope of the exam, things like that. So so this exam covers everything from finite element analysis through wind loads. And visual analysis is included in that scope, right? So of course, you won't be asked to use visual analysis on the exam, right? But you may be asked questions about visual analysis, assumptions, modeling, interpreting results, things like that, okay? So keep that in mind. And then, as I mentioned last time, right, any load tables that you need from ASCE 716 will be provided. So understand how to use those and work with those. Any mapped values will be given to you. You won't have to read anything off of a map. So I don't want you to have to waste time on an exam trying to read a map, right? It's not the point of the exam. As before, matrix math will only be on the exam in the context of solving structural engineering problems. So with this exam, that is finite element analysis. And my promise to you is that all matrix math will be doable by hand. You're welcome to use a calculator, but show the resulting matrices and the whole process, similar to how you did in homework. And so being doable by hand, for me, that means you won't have to invert anything larger than a 2x2, because we showed you how to quickly do that by hand, right? Technically, you can do a 3x3 by hand, but that's not what I want you to spend time on in class. So you won't need to invert anything larger than a 2x2. So that's a clue, right? Think about what that means as you go through these problems when you're faced with them. And if you find yourself trying to invert anything larger than a 2x2, that means you have already done something wrong with the setup, okay? All right, so this goes through more stuff related to visual analysis, and or I guess that's just the note up above, related to finite element analysis. And then the load designation, right, as I mentioned, just through wind loads is on the scope of this exam. So this kind of goes over some of the things that you need to keep in mind as you prepare for the exam and study. This stuff is closely related to things that we talked about at the beginning of the semester, like load distribution and load path, right? So those are inherently going to be included in what you need to know, right? But it's not like a load path problem won't be the main focus like it was on exam 1, right? Now, you may be asked to interpret or describe load paths, and we do, you will be going through that in the context of homework 7 with the wind loads problem. So in that context, you may be asked to do a little bit more load path stuff, but the focus will be on understanding how these loads are determined and what factors influence them, and being able to determine what those loads are, and then how they're distributed through the structure. Right. Any questions? Okay. Good deal. So, with that, we'll continue with snow loads. So, this is now, we're off of the PowerPoint slides, and now we're on to the skeleton notes. So this should be the first page in your skeleton note handout, and it just shows an example of a type of roof construction, all right? Breaking down the surface items, and then underneath the surface you have the roof joists, or maybe it's a truss, all right? So those are spaced at a constant distance of B. So that B represents the spacing. Note that that will also be the tributary width for those joists or trusses, right? And then those joists are supported on one end by a ridge beam and on the other end by a wall. So that's, again, just one example of a type of roof construction. On the next page, there is a breakdown of how these loads would be distributed in our analysis, all right, to a joist versus a truss. And it's a little bit different depending on which one you're looking at. So if we have a roof joist, all right, you're going to want to find the distributed load that is perpendicular to the length of that joist, right? We want the transverse component of the snow load, because that's what determines the internal shear and moment, right? So that's what affects the beam behavior. And then there will also be an axial component, all right? So that's going to be the component of the snow load that's parallel to the joist. And so that's something that you also need to think about and consider in the design. For a truss, we don't have to do that. It's a little bit simpler. All you need to do for a truss is take the horizontal projection of the snow load, right? And it's going to be the same. That part is going to be the same regardless of whether you have a joist or a truss. That's just a gravity load, always in the vertical direction, acting downward. But for a truss, you just take that and you identify the tributary width of the points or the joints on the truss, right? Because remember, with trusses, we assume that loads only act at the joints, right? So even though in reality, it will be a distributed load along the top chord, in most cases anyway, you could configure it so that it's only distributed to the joints in reality, but regardless, we treat it as though it's only point loads at the joints. So you identify the tributary width for each joint and then calculate what that point load would be and apply it like that. So it's a lot simpler to distribute snow loads to a truss. In the example that we're going to look at, we're going to focus on a joist example, all right? So here, let's see. So there was one thing in here that I wanted to correct, and I have to look at my notes to remember what it was. So give me one moment here. Thought I had it. So that was so down here, this WS, that should be a WT to be consistent. So here the N is for normal or perpendicular to the length, and the T is for tangential. So it's a little bit confusing because we also use transverse, which is a synonym of normal, but tangential means parallel to the length. Oh yeah, and I have some more fun pictures and things to show you too after we get through the example. Time permitting. All right. Good. All right, so this example we're going to look at is focused on a roof of an apartment building in Boston, Massachusetts. We're given the roof slope as 8 inches of rise on 12 inches horizontal. So on a sketch, that would look, right, maybe something like this. It's a little bit exaggerated for the slope, but it's probably close. All right, so something like that. So this location marks the ridge. It says rafters span 15 feet. So the span, remember we talked about this at the beginning of the semester. We defined span. It depends on the context, but it can be used as the horizontal distance between supports for gravity loads like this. So that would be a 15-foot horizontal span. And the spacing is 18 inches on center. So that tells us that our tributary width for a typical interior joist will be 18 inches. We're also given some more information about the roof material and the surroundings of the building, all right? So we say the roof is shingled, and we have coniferous trees that are planted around the building. There are no adjacent structures, though. All right, so we want to find the force acting on a typical rafter based on all that information. So first we're going to start with the flat roof snow load equation, all right? So we have our PF is 0.7 times CE, the exposure factor, CT, the thermal factor, IS, the importance factor for snow, and PG, which is the ground snow load. So for the ground snow load, we have to seek out the map, the ASC 7 map, or we can use the ATC hazards website, right, if we want a more accurate reading. So we'll jump over to that. Now, last time we looked at this in the context of seismic loads, all right? But if you look up here, there's different tabs for other types of loads. So for snow loads, we got to put in our new information, and we don't have an exact coordinate, so I'm going to use search by address. And we also don't have an exact address, right? But you can be vague and just type in Boston, Massachusetts, and we'll get, if it decides to cooperate here. Search by address, Boston. All right, so it's giving me an error here. Let me try just refreshing the page, actually. All right, so if we go to snow, enter address. There we go. Boston, Massachusetts. All right, so we land on Boston. If you select, all right, and 3 options show up. These are just different versions of ASC 7 standard. The one we're using is 716. So if you select that, then it'll show you the contour lines on the map. So we can see, if we zoom out, this whole stretch that's shaded has 40 PSF for the snow load. All right, and I'm curious, actually, if we use a different one, will that section change? It doesn't. All right, so that part hasn't really changed in a long time. All right, Boston has had 40 PSF. So that's what we'll work with. And we want to cite where we obtained that information. So that would either have come from 7.2-1. You can confirm that in your handout. Or ATC hazards tool. The importance factor for snow, if you look at the table on the front page of the environmental loads handout, you can see that. We need to identify the risk category. What risk category would this structure fall into? What do you think?
2.
Yeah, risk category 2, right? So most buildings fall into risk category 2. So our importance factor is going to be 1. And that comes from table 1.5-2. All right, so now it'll get a little more interesting. Our exposure factor, if we look at, let's see, I don't think I have those. Yeah. So if we look at the, here we go, pull that up. The last page of the environmental loads handout, all right, we've got this exposure factor. So we need to identify the surface roughness category. So based on the description that we were provided, what surface roughness category do you think would apply here? It's an apartment building in Boston, Massachusetts. No adjacent structures, coniferous trees planted around the building. That really is more related to exposure of the roof. But just based on the fact that it's an apartment building in Boston, Massachusetts, what would you put it in? B. Yeah, I would say B as well. And notice that, I think we talked about this before, even though the exposure or the roughness categories are the same that we use for wind, the worst case scenario was exposure D, right? For snow, it's the opposite. The worst case scenario is exposure B, because the more sheltered or, the less exposed it is, I would say, the less likely it is that wind will be able to blow the snow off of the roof. So you can see that B has the highest factors in the table. So now we have to identify the exposure of the roof. So based on the description provided that we have coniferous trees planted around the building but no adjacent structures, what would be an appropriate guess?
That's it,
Partially exposed? Anyone think something different? So partially exposed, it very well could be. And this is kind of where engineering judgment comes into play, right? So for risk category B, partially exposed, we would have a factor of 1.0. The argument could be made if you had more information that it would be sheltered, right? But because it doesn't say that the coniferous trees are planted closely around the building or like really closely encompassing the building, I wouldn't go with sheltered. I would go with partially exposed, okay? Although sheltered is a more conservative guess. So if you really weren't sure, you could lean conservative and go with sheltered. But in this example, I'm going to go with partially exposed, and that gives us a CE factor of 1. So we'll say terrain, category B, and partial exposure. And that's from table 7.3-1. All right, so thermal factor. Back to our tables. What value should we use from this table, do you think?
1.
Yeah, 1. So all structures except as indicated below. That's going to be most buildings. We don't have something kept below freezing, right? It better not be. That's a liability issue for the owner of the apartment, big time. Shouldn't be unheated in open air, right? So none of those things apply. So that's just from table 7.3-2. All right, so now we can calculate the flat roof snow load. All right, so we got 0.7 times 1, 1, 1, and 40. And that gives us 28 PSF. All right. Now, do we need to check the ASCE minimum values for low or flat slope roofs? I see some no's, some yeses.
Steeper than 10 degrees, right?
Yeah, it's definitely steeper than 10 degrees. So the ASCE minimums don't apply. Those are only for lower flat sloped roofs. Specifically, that was, was 10 degrees the cutoff, or was it 15? I have to look back at my notes. Believe it or not, I don't have all of these memorized. So. Let's see. Where did I put it here?
It's 15.
Yeah, it's 15. Thank you. Yeah, so if it's 15 degrees or less, then you have to check the ASCE minimum. We're above 15 degrees, so we don't have to check that. So I'll say slope is greater than 15 degrees, so the ASCE min does not apply. All right, so now we have the slope factor to think about. So here we go to this table, all right? Now, which of these three charts should we use?
Use the warmer one, right?
Yeah, the warm roof one with, because that's exactly right. So I know it's a little bit hard to read on the screen, but remember these are based on the thermal factor. So for a warm roof with a CT of 1 or less, we use this chart. And then do we use the solid line or the dashed line? Right, we use the solid line because it's a shingled roof. And so since we were given the slope as 8 on 12, that's this right here, we just take that and read what we get from this chart. All right, so that looks like right about 0.9, okay? So we'll use a slope factor of 0.9. That's from figure 7.4-1. So the slope roof snow load, which is going to be the design roof snow load, will be 0.9 times PF, which was 28. So that's 25.2 PSF. All right, so that is our design snow load for the roof. That is something that you should check against any local requirements, all right? I already did the checking for Boston. Boston doesn't have any additional requirements for snow loads, no prescribed minimums other than what we've already seen. So after checking that, you can conclude that this is the design snow load for the roof. All right, so when we talk about things and say, what is the design snow load for the roof? This is what you're looking for, something in PSF. If you were asked to find the design snow load for a typical interior joist, then you would want to report that in pounds per linear foot, unless it was asked specifically for PSF, right? So you want to kind of tune your answer to the appropriate distribution in units for the given element that you're asked to consider. Thinking back to live loads, and since you're dealing with live loads on homework that's due on Wednesday, right? One of the problems asks for the design live load for a floor, right? So that would be, if it's just general for a floor, you don't do any reductions, you just find the value from the table and report that, right? So that's your design live load for a floor. Because remember, reductions for live loads are on a case-by-case basis, like one element at a time. You can't reduce something for the entire floor. So when you're looking for a live load on a specific column or a live load on a specific beam, that's when you would go through the process of identifying, can this live load be reduced? If so, how much can we reduce it based on the tributary area of that specific element, okay? So I just wanted to throw that out there because I figure that might be helpful bit of information for you as you work through that problem. All right, so continuing with this example then, now that we've identified the design snow load for the roof, we got to continue and get the stuff for the rafter. So if we want to sketch what's going on, all right, we can sketch our roof profile, something like this. And then we can sketch that snow load as a vertical load acting over the horizontal projection of the roof. All right, 25.2 PSF. So for the loading on a typical rafter, we need to identify the tributary width, which we already did verbally anyway. All right, so the width is 18 inches. So that means that the distributed line load is going to be the surface load times the tributary width. We want to make sure that we are using appropriate units throughout our calculations, so we got to convert that trib width to feet. All right, so we get 37.8 pounds per foot. So this would be the design snow load for a typical rafter. All right, so now we're going to assume that this rafter is simply supported, right? It's not stated in the problem, but based on the description of the roof, we can assume that's a very common configuration for roof rafters and joists. So if we just consider one rafter then, and we have identified the line load, right? So WS in the direction of gravity. If it's simply supported, that means we're going to have a vertical reaction at each end. All right, there will also be a horizontal reaction, but what's that horizontal reaction going to be?
Zero.
Zero, right? Because there are no horizontal net forces acting due to the snow. And so we need to identify the length of that rafter. We were given the span and the slope. All right. Let's see. Seem to be missing. Oh, there it is. All right. So first, let's go ahead and calculate what those reactions are, the vertical reactions. We can sum moments about the left end. All right, or recognizing that we have symmetry, okay, it's symmetrically loaded and symmetrically supported, you can calculate the total force, right, the resultant force due to this and divide it by 2. Either way is fine in this case. If we were to sum moments, it would be like this. So we'd get a reaction of 283.5 pounds. And summing forces in Y then would also give the other reaction of the same magnitude. All right, so now we need to break this into the parallel and perpendicular components. So the parallel force is what causes axial forces in our rafter. And the perpendicular component causes shear and moment. So the forces acting on the rafter, if we were to break this down, we have the resultant force from the snow load. All right, we'll call that Fs. We're going to break it down into the tangential, which is the parallel component, and the normal. And they will always be acting, right, in the directions that trend downward. So the normal force will be perpendicular, acting towards the roof, and the tangential will be parallel, acting downward. So again, we'll go ahead and say we've got our length here, L. The span is 15 feet. So if we want to find the angle, right, we can do that. It would be 34 degrees. So we can calculate the length then. That would be 37, sorry, wrong number. The length would be 15, right, the span, divided by cosine theta, which is 18 feet. The resultant snow load is just 37.8 pounds per foot times the distance over which it acts, which is 15 feet, right? Not the length, but 15 feet, the horizontal distance. And that's 567 pounds acting downward. So the tangential component is Fs sine theta, which would be 317 pounds in that direction. And the normal component is Fs cosine theta, which would be 470 pounds in that direction. So what we're interested in ultimately is the distributed load that acts perpendicular to the joist. All right, so that's the Wn. So Wn is going to be the normal component, the resultant, right, divided by the length of the rafter. So we have 470 pounds divided by 18 feet, which is 26.1 pounds per foot. All right, so we kind of did this the long way, right? Because what is Fn over L? This is also Fs cosine theta divided by d. Divided by d. L is 15 over cosine theta, right? So, you know, you can work with that as well. All right, any questions? Okay. Now, the other example, I'm going to post that on D2L for you to work through. I can post a recording of it as well, of me working through it. This one will also demonstrate how to break down the axial load. So this one's going to look more specifically at, right, taking this, right, so it's kind of picking up where we left off with the last example, except it's different numbers, so a different context. But from this point, right, determining what the transverse load is distributed along the length of the element, you can use that to draw shear and moment diagrams, okay? And then from the tangential component, you can figure out the axial force distribution along the length. So because the true tangential component of the snow load is distributed, right, similar to the normal component, what you're going to end up with is an element that is in compression down at the lower end and in tension near the top. All right, so your axial force internally on this element at both ends will be the same magnitude, but it's going to be compression down here and tension up here, okay? And then in the middle, it's going to be zero axial load because that's where it's going to be evenly distributed above and below, okay? So this example will go through that process. Since you're familiar with shear and moment diagrams, I'm not going to spend time in class doing it, but I do highly recommend that you go through it, this example. I'll post a recording in case you'd like to follow that as well. Because it's a little bit, different when you apply it to a sloped member, just that we're using only the normal component for the shear and moment diagrams and so on. Okay, questions? All right, so I'll note that'll be on D2L. I don't think I've posted it yet, but I will be sure to post it. Also along those lines, as you prepare for the exam, make sure to check out the extra practice problems and examples that are posted for those topics. So there are a couple for finite element analysis on there. And then I will add one that is related to wind loads that was actually a previous exam question. So you can see how I might shorten a problem for an exam, okay? So that'll be an example for that. And that wind load problem, there's a video, it's a video example. So I'll find the recording and post that for you. It's not gonna be on YouTube though, it's gonna be through Panopto. So just as a heads up, you'll have to log in and do all that song and dance. Okay, so with the remaining time, I have a few fun things to share related to snow loads. So we'll start with the stuff I have on my iPad. All right, so some of you will have seen this, or I showed this in the dynamics class last semester, because this occurred just last winter, and we were talking about it in the structures class at the same time that we were talking about snow loads, I think. So if this will cooperate. I just had it up here. Here we go. So that's just an enormous amount of snow, right?
Oh my God.
I think the rest of the video is just a loop of that over and over again, but it's massive. So you might be wondering, what is the snow load associated with that?
Oh my God.
Well, we're gonna look it up. So I'm pretty sure this was just last year. Yeah, March 2023. Yeah. So that's when they got all that snow, and it was just insane. So the town of Truckee has a whole web page dedicated to snow load design. And here you can see, and a lot of towns and cities or jurisdictions will have something like this, especially if there's significant snowfall and snow loads to consider. So here, it starts off saying, citing the CBC, which is the California Building Code, and it also cites the report where all of this data comes from. So then this is really cool. I haven't seen any other jurisdiction have something like this, and hopefully it will work with this setup here. I'm not seeing the grid lines showing up, but basically, when I open this on the computer, you'll see grid lines. It looks like an AutoCAD overlay on this map, and you'll see all the individual lots outlined. And if you tap on, so it'll show up. We're not seeing the grid overlay. But if you tap on any individual lot, it will report the snow load. So for this particular lot, it's 249 PSF, but they vary a lot over the town. So that one was 249. If we go over here, that one is also saying 249. I wonder if that's a coincidence or no, I think this just isn't functioning properly. So that's unfortunate, but if you check this out, if you're curious, it's interesting to see. They will change like from one neighbor to the next door neighbor will be a little bit different, maybe just by 1 PSF, but still that's how specific they get here. And the range that I saw was like between 200 and 400 basically in this little town. So that's a pretty significant range. And it's interesting to see, how they outline that and specify it. So if you were, designing or building a house in Truckee, you would have a very specific snow load just for your property and your lot. It's kind of interesting. All right, so it's too bad that it's not functioning properly on this system. But if you want to check it out, I'll post the link. You can go to the website and play around on it. But all right, so I think that's all I had up here. So I'm gonna switch over then to the doc cam because I have a few other things here to share. I'm pretty sure I don't have it electronically. Let me quick check. Yeah, I don't. All right. All right, so anyone recognize that building? It's in Oregon. Mount Hood, it's Timberline Lodge in Mount Hood. So this was made famous in the Nicolas Cage movie, The Shining. Or I don't know if it was made famous then, but it's well known for being featured in that movie. And this is a historic structure. It was built in the 1930s. And that was back in the day when the architect and the engineer were like the same person. So I actually did an investigation into potential retrograde or upgrade of this structure. So I got a chance to look at the original drawings, which was pretty cool. And I'll see if I don't have any of them with me. I'll have to track it down, but it was kind of funny because they actually had little stick figures of skiers in some of the drawings. So it's interesting to look back at those old things and see how they were done in the day. But you'll notice, right, the very, very steep roof on this structure, and that's because they get so much snow there that they have to build out temporary structures, right, to just make the building accessible from the front entrance. So this is a picture from back in the day. I don't know when this was, but you can tell it's old, and they've clearly improved their process for making that entrance accessible. And the other thing I like about this picture is you can see skiers skiing down the roof. I don't know if they'd be allowed to do that today, but I think that was kind of fun to see. So anyway, moral of the story, steep roofs, good for heavy snowfall areas, of course. You then do need to consider, though, you need to think about that buildup of snow and the pressure, the lateral pressure that it can apply to the walls of your structure, right? So that's definitely something that you would need to think about in a situation like this when you have a steep roof or a roof where snow will slide off. It has the potential to build up, and that can have structural impacts, but it can also have other impacts as well, right? Related to snow melt and water and things like that. So those are all things that need to be considered with snow. But that snow load, I believe, amounts to, I think I had it written down here, the Timberline Lodge. Yeah, so the snow load for that location is 630 PSF. I think that's the ground snow load, right? So that amounts to about 7 feet of snow. So pretty significant. All right. Are we out of time? We're out of time. All right. So I have one other fun thing to share, but I'll do it on Wednesday. Well, thank you for your attention, and feel free to pick up a hard copy of the skeleton notes that we'll use on Wednesday. First come, first serve. And I will see you all then.